So, hello, hello guys.
Hello, everyone. Welcome to the 2025 High School Engineering Design Competition hosted by the Mars Society. Today, we have our final day of the competition, the defense of our critiques from earlier in the week. First up, we have Team
Soraya Academy 1.
Soraya Academy
Um,
1. You have the floor.
Thank you. Thank you so much, Nicole. Today we'll be starting with, so the layout of this presentation is going to be addressing some critiques that were spoken on Wednesday and then some argument strengthening. This is just going to be addressing some questions that were proposed to us on Wednesday. So one, addressing critiques. So the first critique that we received was the fact that the landing was Jezero Crater. However, this is false information. We said in our presentation that we'll be landing at the Milankovitch crater, and the reason we decided this is because there is significant amount of ice beneath the surface, and in these images we can see that like near the green part of the area, which is where Jezero Crater is, um, it averages around zero point 0.5 to zero point 0.6 depth of ice. So that's where ice is below the surface and also how much ice is below the surface. It gives us a rough estimate. So that's the ideal place of landing. And in the right image, you could see a 3D map of the Milankovitch crater and how it's a wide enough area for us to land and do the things that we need to do. So this is a quote because another one of the critiques was about there not being any water present in the Milankovitch crater. However, we chose this location solely because of the research we've done over multiple days. We figured out that Milankovitch crater was the best area to land because it contained adequate amount of water in the form of water ice. So I'm just going to read this out. So the research done on the Milankovitch crater says that, or indicates that, the presence of subsurface water ice, particularly in the straight walls of triangular depressions facing the pole. This ice is considered to be relatively pure and close to the surface, with a thin layer 1 to 2 meters of regolith covering it, making it accessible for resource extraction. So again, there is ice present under the Milankovitch crater, and that's why we decided to land here. However, in certain parts of the years, because of extreme temperatures, we do have additional water sources, and this comes from ice extraction from hydrated minerals and hydrated substances found on the surface itself. So if direct ice extraction fails, we do have water from gypsum, clinoptiloti, zeolite-bearing clays, and thermal dehydration or decomposition. And these are just some images of the minerals that we plan to extract water from if direct ice extraction fails. So the next critique was about like timing wise, where would the astronauts be staying when the habitat is being built by the rovers, by the hydraulic lifters, and the robotic arms. So the astronauts will be staying in an inflatable colony for the weeks it takes to develop the habitat. And the habitat is obviously developed by hydraulic lifters, welding, and assembly robotic arms, as you can see in the third bullet. This idea was actually proposed by NASA 20 to 30 years ago. It is called the ISS Transhab architecture, and you can see through the arrows the different parts of this architecture and how easy it is to set up. So this will be temporarily what the astronauts will be staying in when the habitat is being built. And usually the habitat, according to our design, would take around 1 to 4 weeks to be built. And the habitat offers a temporary solution for the Marsinauts to stay in. And obviously also has the radiation protection that the habitat offers, but it will be in a temporary form. And the design is capable of staying and hosting astronauts for 1 to 4 weeks. Another critique that was mentioned on Wednesday through email was how will we actually be deploying rovers off the shuttle and off the main ship. So right now two uh, we have two main solutions. One is airbag bounce landings, and the second is sky crane And really, these solutions depend on the mass of the rovers. For example, lighter rovers, which are less than 800 kilograms, will be using airbag bounce landings, whereas heavier rovers close to the range of Perseverance and Curiosity, those rovers are going to be deployed via Sky Crane, and I'll explain a bit more about them later. So first, launch-wise and cruise-wise, we'll be using a Hohmann transfer orbit, and typically this is what NASA and space organizations use to deploy missions to Mars because it minimizes the thrust and fuel that is needed in order to get our rocket into space and deploy on Mars. And the reason the fuel is mitigated is because we use the orbit. The Mars and Earth are closest in this after the 26-month period, so we use the orbit mechanics between Mars and Earth to limit the fuel required. So it's kind of like a catapult. The rockets catapulted around the uh, the field of Earth and Mars because it's optimized in the 26-month period. So that's why we'll also be deploying at 2035. Our mission will start in 2035 and go to 2038, and this encompasses getting the astronauts to the site, 1 to 4 months of building the habitat, the 1.5 years of the actual mission, and then coming back to Earth. So as I said before, airbag bounce landings are for lighter rovers, and the lander bounces across the surface, and they'll be inside airbags, and the airbags are carefully designed to take hits from the surface, and then it comes to a rest where the rover will drive off after. The second method is sky crane, and as I said before, this is for heavier rovers. So what happens in this case, as you can see in the image, this was deployed for the Perseverance and Curiosity rovers because they were heavier. The parachute slows descent, and the descent stage involves a jetpack with 8 engines, and then the rover itself hovers around 7.5 meters above the ground, and then it's lowered with these strings that you can see in the images. Ideally, there will be three, and we'll be using three in our design and research paper. And then the rover is being lowered by these three tethers, and then once it reaches the surface, sensors will detect that the rover has reached the surface, the strings will be cut. So these are the two different ways we'll be deploying our machines onto the surface of Mars. Our heavier rovers will be deployed using the sky crane method, and our lighter rovers will be deployed using the airbag bounce landings. Next, there's a question on solar array dust and how we'll be, so basically our power source is divided into, it's a dual system. We'll be using a kilopower system, and then also for a backup, we'll be having a solar array. And the question that arose was, um, how we'll be mitigating the effects of dust on the solar arrays, as Mars is generally a dusty area, and then dust will accumulate onto the surface panels, solar panels of that we'll be using as backup. So the first mechanism we'll be using is piezoelectric vibration system, and the second is electrodynamic slash electrostatic dust shielding. So really, the electrodynamic and electrostatic dust shielding will cover around 90% of the dust, and then we'll be using the piezoelectric buzzers to get all of it off, 100% of the dust off the solar panels. So how do they work? And the reason we chose these methods specifically was because we didn't want these windshield wipers covering the solar panels because we want optimized energy retrieved from the sun. And these buzzers will be detecting dust when it falls onto the solar panels rather than a windshield wiper being there and every 1 or 2 hours just wiping away. And we want to optimize the energy that's retrieved from the sun. So how do they work? They were proposed by NASA in the NTRS technical report. And what we do is we attach these buzzers to the panel, and once they detect dust, they will periodically induce vibrations. This obviously doesn't require any wipers, and the dust loosens and slides off when the panel is tilted at a slight angle. And just like an analogy, this is kind of like the vibration. So say you have a pan, when you tap the bottom of a pan, you induce vibrations to it. And if you want to get dust off of it, if you tap the bottom of the pan, the dust no longer sticks to the pan as it once did, and therefore falls off. The second method that we use is electrodynamic electrostatic dust shielding. This was developed by researchers at Boston University with NASA support. It's it's a solar panel, but it's covered in a transparent electrode layer. The reason it's transparent is obvious. We want to get the sun's rays cannot be shielded from the solar panel itself. So the material we use generally is indium tin oxide. Then, when dust reaches a threshold, the sensors trigger an alternating electric field wave across the surface. This repels the dust particles and then pushes them off. And again, this method would generally be used first, and then the piezoelectric buzzers would be used second in order to ensure that all of the dust is off the solar panel. Then another question that was brought up, I think it was in a meeting on Wednesday, was there were no systems in place to help the current operating rovers. This was a question proposed by Team Solace. And I want to emphasize that rovers generally operate for extended periods of time. For example, Curiosity has been exploring since 2012. Perseverance is performing its experimentation on the surface of Mars since 2021. And then helicopter Ingenuity was only scheduled to fly 5 times, but it's now flown 70 times. And over the course of its flights, it's been taking images, it's been sampling the surface, it's been sending data back to Earth. So obviously, these machines and these rovers have been sampling the surface of Mars for a long, long time, and that's because of their intricate and accurate and efficient designs. And our mission is only 1.5 Earth years, so we are confident that our missions can do the same as these big organizations. Um, and because we have designed it with accuracy and designed it with precision, and we have 3D modeled it using AutoCAD and Fusion. Second is argument strengthening, and we just have two main slides for this. Uh, so this is in response to a question actually it was proposed. Since Mars is a dusty environment, this is the question. Since Mars is a dusty environment, do you think that the surface of the Mars and the dust on the Mars would impact the inflatable habitat in any way? So first of all, this is the basic habitat design. The frame is from stainless steel and it's coated in a 5 millimeter thick aluminum oil alloy. And this emphasizes flexibility and also strength. And it being inflatable means that it has a internal volume. It's 675 meters cubed, and this is sufficient for the astronauts that we decide to bring on the mission. So if students are confused as to the strength and flexibility of the material, one is that there's a steel frame put in place before it's coated in the radiation protection. So the radiation protection is in four parts. One is HBNNT, and this is BNNTs enriched with hydrogen. Then there's polyethylene thin film, then carbon nanotubes, and then aerogel. So what this does, this is not only neutron absorbing, it also has heightened shielding capabilities with added hydrogen. It's an encasing mold over the steel frame that was originally there in the habitat. It's also incredibly flexible and pliable. It has heightened insulation from the aerogel, and it has low density because of the carbon nanotubes and the aerogel. And then it also has resistance to flex fatigue by the carbon nanotubes. We don't want rigid structures. That's what we've been trying to emphasize in our research paper because Mars' atmosphere is definitely unpredictable and we don't want rigid structures to crumble under. We want adaptable structures that are able to resist any changes in the environment. So last point, resistance to flex fatigue. This is basically as the carbon nanotubes bend, they are able to retain the same amount of strength that they had prior to bending. And this is incredibly important in our design, mission planning, and overall sight and vision for the deployment. So yeah, that's it. Thank you so much for listening. And yeah.
Very nice defense. Very nice defense. Thank you so much. Is anyone from Team Soraya Academy 2 in the room? Okay, we will wait 5 minutes. If Soraya Academy 2 is not available, we will go straight to Team Solace. So we will begin in 5 minutes. And if you have any questions, feel free to ask in the chat. I did put in the chat earlier the links to the previous year's presentations, the first year and the second year, are published in a book. If you'd like to look at the previous presentations, you may purchase those. If you cannot see those links, please let me know and I will repost them. Mohammed, you are Soraya too? Okay, you're
Hello,
ready?
Mrs. Nicole. How are you today? Yes, I'm ready now.
Okay, go right ahead
Okay.
and go right ahead and start.
Okay. Um, Mrs. Firstly, as we can show in this screen, our team, Sarah Smart School Team 2, have a lot of things that we should defend about it. And the first thing is the electronic suspension feasibility. As we can talk about it in the multi-mission space exploration vehicle or MMC, about the active suspension. Our active suspension can get it from a mechanical suspension or mechanical system to electronic system, about a new mechanism that can be or that can do it carefully from and we can take it from the RC car, and RC car is not the is not the mainly vehicle that we can depend on it. We talked about it because it have a lot of servo motors, a lot of electronic things or electronic um, uh, components that we can depend a lot about it, uh, just like the servo motors that can be different from or instead of the mechanical dampers and the dampers and springs that will be give a straight or a straightly movement instead of these springs, because the springs have a lot of displacements that make it not efficiency um, uh, different from servo motor. So this is the first thing that is very important. And the servo motor is a closed loop system, so it can give it movement from its closed loop from the resistor that have in it, from the system that give the input, and that it was the force, and give it to a fixed movement that can depend on it a lot. And this movement will be fixed and precise on its degree, on its truly degree. So this is the first important that very important. The another thing is about the kilo power system that we can depend on it. And as we can talk about it, is the kilo power can make it more specifically. So if we can talk about it in this section. Okay, so in the kilo power system, firstly, we will do, or we will put motors or another type of motors that different from our motors that we can use it a lot, like servo motors and DC motors, DC enable motors. This is another, or this is a new type of motors that we can take it from YASA, and we can depend on it in our study, because it has a lot of things. The firstly of these things is the direction of the magnetic field. Its direction of this magnetic field, as we can see, is axial, not radial. So this axial movement make it very efficiency, and have a very few or a very small of yes, sorry. Now I share the screen. Yes, make it have a lot of very small of energy, so it make it very efficiency. Have very efficiency, a lot of fuel, power consumption. So yeah, uh, we can offer an increasable or a very sea of increasable um, um, uh, torque in this movements in the movements of these motors about 400 the combinal or the oldest motors. So this is very important thing that we can show it. And as we can see, we can show the difference between the two motors, the radial flux and the axial flux technology. And both technologies, YASA use it a lot in this in their section. So yeah, this is very important, and radial flux technology currently in all production EVS, and as we can see, it have 40 Newton meter by L or by low by left, and have 2050 bhp as a force, as a velocity. So um, the axial flux motor, as we can see, yes, there in YASA, uh, will be work in 10 kilowatt over the kilograms, and it is very high than the combinal or the technical old motors or radial flux motors that we can use it. Okay, and why YASA? Why YASA or why Magnex? Because it has a lot of things or advantages that make it very efficiency. Okay, so this design of these motors, it will be closed or it will be remove the dependency to use yoke or to use this magnetic yoke or yes, magnetic yoke. And in this fixed, if we can see in the fixed motor, not in the rotor, in the fixed, up to or up to the motor, um, making or the open, if we open the motor inside this motor in the fixed, not in the rotor, we should we can remove this yoke or minor yoke, and that will be reduced from it will be reduced from the its force or its its magnetic field about 80%. So what about the two first things or the two important things about the consumption of the power consumption, that we can show it a lot. Okay, no matter what the road brings, as we can see of this, we can realize that YASA axial flux motors give up to and the YASA motor topology. Its topology, and as we can see in this figure, the force, when the force make make stand or make a fixed or applicate a fixed in another on in a particle direction. This direction will affect on the diameter of the magnetic Fe, and this R or this radial will be give its directional or give its position with theta, so R sine theta, and it's opposite with the it's sorry it's uh, yes it's with F and with opposite of with F make the torque or give me the torque the torque function. And in the axis of the rotation, this will be increased or this will be show the same force or the same directional of force, the same of this force. It's directional and it's numeral yes, and it's numeral or numerator thing. And if you can see, it's smaller than the other rings things, and it's more useful than, and it's have 50% less.
Oh no. Let's wait a minute and see if he pops back on. Were you done, Mohammed, or did you have more to present? You're muted, honey. Unmute yourself.
Sorry, Mrs. How are
No
you?
problem, no problem. You have more
Yeah,
to
I
go?
have a bad connection, so I will. Can I continue about
Yes.
some things?
Yes.
Yeah. We'll talk before that about the motors or the YASA axial motors and what is difference between radial and axial. So as we can see, this axial will be make or will be have a less power consumption is under of 50, 40, or 30%. So it maybe cannot bring or consumption a lot of or consume a lot of power from the kilo power that maybe can 10 kilowatt as a standard power. So this is the main reason to use the power or this kilo power to bring a lot of relaxation in our vehicles or um, uh, in our technical things and technical vehicles that will be moved on our environment. Okay, and the second thing about that is the consumption, if it can be very high. So simply, if the consumption of if the power consumption that we can use it is very high, we can make a matrix of kilo power system, a matrix of a matrix from kilowatt, from 10 kilowatt or from 5 kilowatt system. That's not very difficult thing. And we can show, or we can take a very note, and we will depend about it a lot in our file, or in our final file, is we can use from quantum, or from a company that have a name called quantum, or quantum scope, annually generation of solid state batteries, and these batteries um, can use, or can give its power and its electricity power from the kilopower that will be dealing with the nuclear energy. So these batteries will work particularly, and this will be get the power that can bring it in its batteries, get its power, or bring, or give its powers to the another, or to the other, to our vehicle, to our systems, to our another systems, that such as rovers and our MMC vehicles, to a lot of things. So yeah, this is a very simple way to help how we can consumption the energy that we can use it. And this is all of things are the proposites that can help our to consumption a lot of power. Okay, if we can see after that about the wheels, or the wheels that the wheels that make it, or that the chemical make from, or its chemical materials make from nitinol. So I will show what because of my charging can I show I could show from previous the study in the SolidWorks, that we can show how the wheel, or how the forces that make in wheel that make from titanium or nickel can dealing particularly with this forces that we can applicate about it, on it. So the titanium, or the force that will be applied on the titanium or titanium material will be affect in a lot of red regions above or around the wheel, and that's is very important thing, because it refers to a lot of forces that we can applicate it on the surface of the wheel. These forces are very harmful and will be harsh the wheel. This is with the titanium only. The nickel will be very worstly, because it can be in the harmful things, bring out our wheels from its place, and that's very difficult, very worst things that we can do. So the nitinol maybe, or give the same or the similar the similar amount between the nickel and titanium, to bring other, or to bring both um, the Trolley displacement, and the strength of forces that we can applicate on it because of its movement in the ground. So this is very important things that we can note about it. So the nitinol is very simple, or is very important thing that we can use it on the wheels. Another thing, NASA bring or NASA help us in its studies to show that we can design our wheel or our above wheels surface or circular surface of wheel from the grid, or as we can say on it, wire tire or wire mesh tire. And this wire mesh tire or our design for this wheel of wire mesh tire is very important, and is very thing that dealing precisely with all of the forces that will can dependent on it. This is about the wheels. We can defend about another important things, just like the human recycling or the human resources that we can recycling on it. We not recycle 100% of the human resources, and this is very worst things, because this is 100% meaning that we don't have another sources or any resources of the human that can be or can on the surface of Mars for ever months, ever years, ever days. So this is make very problems or make a lot of problems on the surface of the little planet. So we recycle 70% of the human resources, and the 30% will be under processing or our processing. And the most important thing that we can talk about it is the ISRU and ISRU 2. We cannot use 100% of ISRU, and our token about it in our presentation is a very low is a very paragraph, shortly paragraph can talk about it in the taking of mine water, and this is the firstly thing that we can do if we can be on the earth. So making or using ISRU in the earth in the first few days or first few if we can talk about it very truly, we can take on Mars, or we can take our information from Earth about surely a lot of little months or little seconds to give all of our informations, but this is will be take a few time from the Earth, and all of the processing things that we can do or that we can making it on the Earth from our colony only, or from our colonies. And the 3D printing that we can use it to print to print a lot of things like vehicles, colonies, a lot of things. We can note a very important thing about it, that we cannot print vehicle or print wheels. The nitinol wheels will be given prepared from the earth, and after that will be combined with our vehicle or with our total 4 important individual vehicles to move precisely on Mars, on the surface of Mars. And all of the other things or all of the other equipments that I can should printing it are from or are the colony, and after the colony, the structural about or around this colony, we will print the most important things we can print after that. The equipments that we will fix it in the Mars or in the surface of Mars. So there are a lot of things that We can make an accident if our vehicles make a random or a different accidents for a lot of things or for a lot of reasons. We can take this take this equipments and repeatedly printing it using our 3D printing. So this is very important. Um, we talked about a lot of things like 3D printing that we should defend about it a lot and make or add showing it reasons and possibilities a lot. And another things, just like the kilo power, we can make arrays from the kilo power system to make it very precisely and very make this very individual and important things to consumption or to give a less consumption. We can talk about the motors or the axial motors. We can talk it from EASA or from magnets, and the both companies are very important. Are very useful, and we can take our motors from it precisely. There are another things like the location. As we can say, or as take or as talked about it, our team Genesis team talked about our landing site or surface on the landing site. Okay. Unfortunately, because my laptop has a low charged, can show or I could show a lot of images from the satellites that we can show it precisely and carefully from the GMARS application. And GMARS can show a lot of images from the satellites, from the orbiters, just like Viking orbiters, Viking 1 and Viking 2, that we can show our images like ArcGIS or ArcGIS MDIN 2.1. This image and a lot of images that we can use it most carefully to detect what the regions that have a lot of mine waters, a lot of minerals, a lot of ice exploration or ice to exploration it, ice water, and a lot of things like the deepest or particular or making or detecting the deepest region from the MOLA images. And the MOLA images, we can use it more carefully to take the elevations from our images. So as we can show, we could show from our maps in this application that now and this informations will be charged or will be changed a lot. We can create or we can detect the deepest region in our landing site in Hellas Planitia. And Hellas Planitia, as we can say yesterday, had the deepest region between the water or the ice water and Kafnin or Castnin, between two points of regions. Between Castine and water on or ice or cool water, ice water. So between the both regions, we have the deepest region of about minus 78 and 5, or 7,785. So this is the deepest region in our map, and we can show another things like the ice water, and as I can show it is today, that the ice water will be take it precisely or particularly region on the northwestern polar of Heliosplenetia. I showed.
Mohammed, are you about
Yeah.
to wrap up because we have to make time for the next team?
Okay, Mrs. This is the last thing.
Perfect.
Okay. So this is a region that I have showed it. I have showed in the northwestern pole of the map, polygon of ice water that will be have its shaped to predict it to the ice. But this these things that we can show it from MOLA or from the MOLA maps only don't make it or don't have to our informations about what the water. We should show a lot of another parameters like what the sustainability of the surface or surfacely or the flatness of this surface of the region that have ice water and a lot of parameter things. That's the all of the most important things that I can talk about it. And thanks a lot. And I hope that I notations or I get my notes about all of the things that we should defend about it.
Thank you so very much. That was a great defense. And Team Solace, do you want to go ahead and start, or do you guys think you need a 5-minute break or 4-minute break now?
No, we can present now. If
Okay.
the rest of the team is ready.
Go right ahead.
Okay, I'm starting to present. Ria, please begin.
In the last round, every flaw was illuminated, every crack, every variable, every doubt. And that's exactly how it should be. Because missions to Mars aren't built in silence, they're forged through questions, pressure, and challenge. And what stood the test of your critique stands a better chance on the Martian surface. Today, we don't just respond, we rise, not to defend weakness, but to prove strength, to show that every design, every experiment, and every decision was made with Mars in mind. This is a rebuttal, not as a counterattack, but as a confirmation. Our mission is ready for Red Planet reality. Let's briefly highlight the core differences between a kilopower reactor and a fission surface power or FSP unit, because a few teams have misunderstood that we are using an FSP and not a kilopower reactor. Fundamentally, kilopower uses Stirling engines for power conversion suitable for low power, that's 1 to 10 kilowatt electric, and already demonstrated in the ground prototypes. In contrast, FSP employs a Brayton cycle turbine designed for much higher power, that's 40 to 100 kilowatt electric, intended for surface bases, though it's still more conceptual for development. Crucially, FSP is highly scalable, whereas kilopower units have limited scalability, about roughly 10 kilowatt electric. Moving on to Team Phoenix. For this and the following teams, we'll be first quoting the critique from the team and followed by the rebuttal. One of your critiques were, moving to specific design elements, your plan for terraforming walls lacked explicit equipment or detailed methodology. For terraforming walls, project guidelines did not require specific tool enumeration, Our detailed construction slide outlines processes and methods implying necessary tools within the broader plan. You stated that regarding habitat scale, the depicted habitat appears very large, raising questions about its compliance with competition size limits and implications for mass, volume, and power. Regarding habitat scale, the visual representation of our habitat is accurate. It comprises of 8 models well within the competition limits, and we confirm it avoids issues of excessive mass, volume, or power requirements. Please note, the picture is simply not made to scale, especially concerning inflatable habitat modules. Another critique was, finally, concerning your reactor, there seems to be a misconception mistaking your unit for kilopower reactor with steam turbines. For the concerning reactor misconception, the critique regarding kilopower using steam turbines is based on a misunderstanding. Our chosen reactor is an FSP reactor, not a kilopower unit. This specific critique is therefore irrelevant to our proposed power system. Another thing you mentioned was on an AI integration, your proposal lacked sufficient detail on the power and processing capacity for your extensive AI. Additionally, we noted a food mass discrepancy, 6,000 kilograms mentioned, but only 3,000 kilograms in your spreadsheet, which needs clarification. For AI integration, full specifics were reserved for our design report due to time constraints. But the required computing power and processors and storage are fully accounted for. Regarding the mass discrepancy, we appreciate the identification of this data transfer oversight and are correcting documentation to reflect the accurate figure of 3,000 kilograms for mission sustainability. I'll now hand it over to Ashwin to carry.
Ashwin, you're muted.
Thank you, Ria. One of your critiques were on crew selection, your balanced gender approach, 2 female, 2 male, 2 merit-based, but purely merit-based raises expertise concerns. Our answer to this is that all our astronauts are merit-based, but our crew selection needs a balanced gender approach for diversity. This is to prevent a gender ratio becoming something like 5 men and one woman. Another one that you mentioned was for hydroponics, you rely on it without highlighting margin soil growth. While hydroponics is our primary method due to proven success, our mission plan includes carrying dehydrated food as backup. These alternatives address the scientific goal of utilizing local regolith, although not highlighted in this presentation. We have planned for margin soil growth, but not only as an experiment, as it has not been tested and can prove catastrophic if it doesn't work. Lastly, the Crystal Haven's weight lacks explicit justification for remaining within limits. We need to acknowledge the mass underestimation in our Crystal Haven design. To address this, we will now be adopting a lesser mass version of this design. This newer version will remove aluminium oxynitrate to bring the total mass within the provided limit. We have meticulously designed a multi-layered radiation shielding system for our Martian habitat, carefully engineered to maximize surface coverage within a 3,200 kg mass budget. Our strategy specifically targets both galactic cosmic rays and solar particle events. This system is comprised of 4 distinct layers. Outer polyimide film. This initial layer is a 25 micrometer thin film, specifically Captain, which provides crucial protection against UV radiation, dust, micrometeoroids. It covers 250 square meters and has a minimal mass of 9 kgs. Second, the HDPE main shield. Following the outer film is our primary shield, made of 12 mm high-density polyethylene. This robust layer is designed for 20 to 25% reduction of GCRs and a significant 85 to 90% reduction of SPEs. It also covers 250 square meters, contributing 2,820 kgs of the total mass. Third, the titanium carbon frame. This component serves as the habitat's structural support. While essential for integrity, it contributes 350 kgs to our total mass and provides no direct radiation protection. Internal MLI. The innermost layer is a 1 millimeter multi-layer insulation. This MLI ensures the habitat's thermal stability and provides EMI resistance. Like the other layers, it also covers 250 square meters and weighs 20 kgs. Together, these layers form a comprehensive shielding solution for the crew. Now, let's move on for the rebuttal for Saraya Academy 1. Your next critique was moving to landing and operations. Your chosen landing site includes surface obstacles that would impair rover movement, with no assessment of navigability or terrain risk provided. Our landing site, we selected flat valley floors in Deuteronolis Mensae for safe landing and optimal rover navigability. Scientific sites are within 200 to 500 kilometer safe radius for EVA access, with easy roads. Also, the Aries Scout 1 drone will be used for scanning terrain level differences. You also stated that your surface power system lists a 40 kilowatt power output without specifying a relevant time frame, such as per hour or per day. The habitat will require 35 kilowatts of power continuously, and we are well above that as the FSP provides 40 kilowatts of power continuously. And as a contingency and a method to reduce the FSP's workload, we will be also using solar panels. Another critique was your coordinates are approximate and lack precision, which on Mars can span tens to hundreds of kilometers. Regarding coordinate precision, on Mars, 10-kilometer margin is standard due to mapping resolution and rover navigation limits. Exact coordinates will be finalized by mission control. We provided central coordinates for Deuteronolis Mensae along with approximate locations of specific exploration targets. We will also be using our Aries Scout 1 drone to do more thorough terrain mapping. Trisha, the mic is now yours.
You criticized us saying, addressing hydroponics and diet, your section lacks crucial data like growth times, missables energy units, omits character contexts, and provides no data on lighting, nutrients, or waste recycling. The astronaut diet is defined only by an average macro ratio. There is no need for soil stimulants as we are growing everything using hydroponics. For hydroponics and diet, caloric values are based on 100 grams edible portions, with an average density of 1,482.17 calories or kilograms. We utilize dynamic LED lighting and standard hydroponic nutrient solutions. We apologize for not mentioning spirulina and nutritional yeast growth times, but this will be quantified in the final report. A structured agriculture calendar ensures continuous fresh produce for a 2,500 to 3,800 calorie daily diet. Another critique included this. Finally, the rover design lacks clarity. You mentioned an undefined aluminium 760 frame material, have conflicting wheel counts 6 and 8, and provide no details on steering configuration, suspension type, or calibration. Our rover's chassis is constructed from aerospace grade 7050 T7451 aluminum alloy and TI6AI 4V titanium for load-bearing joints, with carbon fiber composites used in body panels to reduce weight. It utilizes a six-wheel rocker bogie suspension system, commonly used in Martian rovers, for passive terrain adaptation and high obstacle clearing capability. The rover's wheels are independently driven and support differential steering for enhanced maneuverability. This was another critique. For radiation shielding, your description is generic, lacking specific target dosage values, clear shielding assumptions, and differentiation between galactic cosmic rays (GCR) and solar particle events (SPE) protection. Concerning radiation shielding, our plan provides 20 to 25% GCR protection and 85 to 90% SPE protection. Materials include HDPE, a polyimide film layer, a multi-layer insulation layer. An important note here is that these experiments are not core scientific interests and are hence not that detailed. Here are some more of the critiques. First, your Martian sound experiment lacks frequency range, calibration, and clarity on low pressure function. The Martian sound experiment accounts for Martian conditions, using controlled sound sources for baseline acoustics with materials accounted for. The next one was the paper airplane challenge needs instrumentation for aerodynamic data. Observation alone is insufficient. The paper airplane challenge is observation for qualitative insights, not a primary scientific goal. Following this critique was Regolith's canvas lacks compaction, cohesion, or erosion data, and dust behavior empirics. Regolith canvas investigates compaction, cohesion, and erosion via video, not claiming trioelectric effects. The next critique you stated was, finally, dust devil dance fails to define relevant pressure conditions for vortex generation. The dust devil dance occurs in enclosed chambers using simulating Martian pressure, focusing on vortex dust via high-res imaging, with materials accounted for. A few more of your critiques have been included here. First, your shallow ice extraction experiment assumes access to labate debris aprons but lacks crucial details on drill torque, penetration depth, energy budget, and mechanical performance. For shallow ice extraction, we plan extraction from low-weight debris aprons (LDAs) at 44 degrees north and 336 degrees west, drilling to 5 to 10 meters deep depth using our rotary drilled red water drilling system. Recovery efficiency will be assessed by weighing extracted ice via mass sensors. However, we acknowledge that drill torque and energy budget details are not fully elaborated in the current report, and that part of the critique remains valid. You then said the dehydrated mineral water extraction experiment does not specify the high temperatures required, above 300 degrees Celsius, or methods to capture and store released water near the habitat, risking inefficient transfer. Regarding dehydrated mineral water extraction, the report states controlled heating between 150 to 300 degrees Celsius, which partially addresses the temperature critique. The experiment is conducted at a sample lab near the habitat, implying no long distance transfer is needed, and water vapor is condensed and tested, confirming storage and quantification steps are in place. Another critique from your team was, finally, your dust to glass sintering experiment lacks data on sintering temperatures and energy input methods, along with missing assessments of mechanical strength, porosity, and brittleness. For dust to glass sintering, we specify microwave kiln or solar concentrators as energy input methods, with the material intended for windows, lenses, and coatings, implying a basic mechanical utility. However, we acknowledge it was not mentioned in the presentation. We have mentioned this on the slide. And here is a table mentioning our crop yield and caloric contribution for the entire 18 months, including potatoes, lentils, spinach, and microgreens and the rest of the crop that we'll be using. And this is a final output summary and nutritional insight of our mission. Now, to move on to Saraya Academy 2. This was your critique. Moving to agriculture, your presentation lacked important data, and we have questions regarding MOXIE and ROXY. For agriculture, we're unsure what data was missing as we detail crop specifics, caloric values, growth times, hydroponics, and dehydrated food. We will include a MOXIE in our final report, though we're unfamiliar what you mean by ROXY. The next critique was, for location, we feel there isn't enough information provided, and previous vehicles attempting to enter this area have reportedly faced problems. Regarding the location, the Deuteronomus Mense region is extensively mapped by missions like MGS and MRO, which detected subsurface ice. No mission has ever attempted a landing there, so claims about previous vehicle issues are incorrect. Following that, you critiqued our radiation shielding, saying that regarding the Crystal Haven, we need clarity on how its panels will be structurally assembled and a definition of Martian soil properties, especially concerning its role. For the Crystal Haven, our updated design changes the shield from a dome to an additional structurally assembled layer around the habitat. This will provide adequate shielding for a day-to-day basis, with the emergency module for high particle discharge events or others as such. And lastly, the use of aerogel is just a thermal insulator rather than a water healer. The temperature of it will be regulated via standard heaters present in the water tank. Laksh, you now have the floor.
Okay. Now let's review the critiques from Team Genesis. One important note that we have quoted the critiques word by word for this particular team, and that will be followed by our rebuttals. So, you stated that on crew well-being, our presentation lacked details on that and also didn't mention integration with the habitat. You said that a lot of the psychological support system mentioned do not exist and that there are no physical features like private quarters, adjustable lightings, or soundproof areas. We would like to point out that our design includes private sleeping pods, planned adjustable lighting, soundproofing, and comprehensive mental wellness support. Details to this have been mentioned on the slide. More than that, in regards to the ISRU critique, you mentioned that there are no MOXIEs, no tools for digging up regolith, and no mention of systems to recover water on Mars. We would like to say that we have mentioned each and every one of these. We'll be using the red water system to recover water on Mars, and other details have also been mentioned with MOXIE under consideration. Next slide, please. Then, I'll quickly sum up the next few points. You said that the habitat is one big structure. There are no separate sections to handle emergencies like fires, pressure leaks, or radiations. We would like to say that our habitat is divided into 8 distinct modules, ensuring full compartmentalization for emergencies, which each module being sealable and equipped with automatic procedures for fires and pressure leaks. A dedicated self-sustained radiation shielding module complements our Crystal Haven module and serves as an emergency shielding. Then we move on to your next critique. You said that for the food plan, it completely depends on Earth. So there are no greenhouse or recycling methods in your mission, which makes the crew incredibly vulnerable if supplies are disrupted somehow. This is again wrong, as our mission incorporates hydroponic agriculture as mentioned in our presentation. Further, we'll be growing 13 high nutritional yield crops along with sufficient dehydrated food as an emergency backup. We'll be having a completely closed loop recycling system alongside that. To share our basic plan, we'll be carrying 3,000 kilograms of packed food from Earth, but we'll also carry on with hydroponics. Regarding advanced science, you said that the science objectives of our mission aren't clear, and we feel that there were no soil samples, spectrometers, geosurvey equipments mentioned. Actually, to this, we would like to say that we have accounted for over 30 different general instruments, which include the soil samples, spectrometers, geosurvey equipments, and everything else that you stated are not there. More than that, we also have a detailed mass breakdown for each and every one of these instruments, as well as particular mass breakdowns for individual experiments like the special experiments and MARO. Then, finally, for medical equipment, you said that it is limited to an emergency response without vital tools like ultrasound, telemedicine capabilities, or dedicated isolation areas for disease. For this, regarding medical equipment, as clearly mentioned on our slide 48, titled Self-Sufficient Mars Medical Operations, we have explicitly detailed continuous crew health scans via wearables and other tests. We also have lab-on-a-chip diagnostics, along with portable ultrasound and MRI X-ray for high-resolution imaging. Our emergency module and private pods will be used as a containment room if needed. Okay, then we have the final 3 critiques. You said that moving forward, we note a lack of a clear plan for future growth or subsequent mission plans, with no mention of module-based exploration for future endeavors. So while future phases weren't part of the project guidelines, our current mission planning ensures that the habitat and rover are reusable for future missions. All modules feature standard expansion protocols for easy expansion, and our unpressurized rover, as mentioned, will remain operational post the mission. The crew returns back. Then, regarding EVA activities, you said that our mission lacks specific rover or docking stations, implying reliance on long walks that could prove disastrous in emergencies. Once again, across slides 21 to 24, we have explicitly detailed things about EVA activities. Sorry, slides 35 to 38, my bad. And we have explicitly mentioned details on transport vehicles, including both rovers. There has been no mention of long walks or EVAs whatsoever. Further, we have explicitly placed 3 airlocks across our habitat. For our final critique, you mentioned that power systems appear extremely vulnerable due to a single line design with no clear mention of robust backup batteries, RTGs, or microgrids. For this, across slides 21 and 24, we have detailed that our FSP will be a primary power source along with 14 deployable solar arrays for backup and load reduction. We have also provided detailed information on our power storage units in the slide. So, with this, we come to the end of our competition. And Mars doesn't care for perfect plans, it cares for prepared ones. And it will test our hardware, challenge our assumptions, and throw the unexpected at every turn. What you offered us, mirrors this in reality: friction, gaps, pressure points, and doubt. And that's exactly what we needed. So this was not just a rebuttal. This is proof that our mission is not just imagined, it's engineered, forged by critique, mission ready, and shaped for the silence and storms and the surprises of the Red Planet. Thank you, and we'll see you on Mars.
Thank you so very much. Wonderful, wonderful defense presentation. All of them so far have been very, very nicely done. I appreciate all your hard work. Great, great
Thank you.
job. And perfect timing, by the way. Is anyone here from Team Solace?
We were Team Solace, ma'am.
Oh, I'm sorry, Team Genesis. I'm sorry.
Yes, ma'am.
Okay, are you ready with your defense?
Yes, ma'am. I'll just present our screen.
Perfect. Go right ahead.
So, unfortunately, in our team's report and presentation, we did not face a lot of critiques. Only three, in fact, one from Team Solace, one that both Team Phoenix and Team Ares mentioned, and one from Team Ares. The first critique we received was from Team Solace that, I'm not quoting this word for word, your mass is massively underestimated and could prove catastrophic to your mission. We do apologize. We did not put the mass breakdown in our presentation due to time constraints. However, it is right here in this response session and will also be included in our report. Johan, the floor is yours.
Again, okay. Yeah, so this is the second critique right here, which is our reactor deployment. Now, ahead of the main launch, the reactor components will already be transported to Mars along with the detailed instructions and the assembly manual. Now, upon arrival, our team will assemble the reactor on site, ensuring the optimal energy generation to support our long-term needs on the planet.
Amir, over to you.
Yes, Team RS said something about our provision transfer from the hub to the no from the spaceship to the hub. And our idea was that astronauts will first transfer the essential supplies that will help them activate core systems and set up everything for their survival on the basics. After that, robotic helpers will assist them in transporting gear and all the habitat modules because these machines can handle heavy lifting and repetitive tasks. In this time, the astronauts can focus on oversight and system integration, pretty much that everything works well. And once the habitat is fully functional, the astronauts will carry the remaining provisions with the help from the robots. And in this way, everything can be staged and ensure that everything will be okay.
If any team wants to further make note of our weight table, it is right here on the screen. Take a screenshot if you want. Thank you, and honestly, we wish we had been faced with more critiques, since then this presentation would have been much longer.
Absolutely
Thank
no
you.
problem. Great job. This would be a perfect time to take a little break for everyone to stretch their legs, get a snack. Is anyone here from Team Aries X? Anyone at all? Okay, is anyone here from Team Phoenix? Okay, is the yes Aries X or Phoenix? Phoenix. Okay, is anybody so second call for Aries X. All right, so we will, if Aries X is not here, we will start in, let's take about a 15-minute break. And we will start with Team Phoenix in 15 minutes. Okay, so Team Phoenix in 15 minutes. And I'm putting that in the chat to mark the time. And I will see you guys all in 15 minutes.
All right, hello everybody. We're glad you're here for our presentation on our responses to the critiques that were given to us on Wednesday. We decided to make a more refined presentation this time, and we're going to go over team by team and respond to each one of the points. I think we may have missed a few, but we're just going to work through it one at a time. So, beginning with Team Solus. Quick overview here. They do make a few valid criticisms, but some of them kind of seem to overlap or don't make any sense. So we're going to start here with the claiming that the life support is a single point failure system. And we believe that this is a kind of a given in any sort of space environment. We can't afford to bring a backup life support system. That'd be far too heavy. Instead, we're going to focus on keeping it as safe as possible and preventing any kind of shutdown. You also claim we have a lack of backup power, even though we clearly specified that nuclear power, specifically 10 kilowatt kilopower reactors, are our backup, which can have their output controlled by a control rod. And this later, you're going to mention that we have too much backup power and that's a waste of mass, so we're a little confused why you said both. The next thing you said is that our HAB needs thermal control, which it has. We mentioned that in the presentation. But it's true that we did not mention things like puncture risk, though the whole habitat would not collapse, even in the event of a tear in the outer layer because of the defensive polyethylene layer in between the habitat and the Vectron inflatable. You claimed our rover was pointless because it only served as a scouting instrument. But we do want to point out that orbital scanning of the surface of Mars versus people actually on the surface are entirely different things. Sample collection, close experience. We can monitor things more closely. Those are two very different things. And we also did explicitly mention that the rover has drilling equipment that is stronger than our autonomous rovers. So scouting is not its only purpose. We're going to go through 3 here. You mentioned that we had no pre-scouted sites. While we did mention Elysium Mons as a potential research location, we should have mentioned Elysium Planitia as a whole. You said we gave too much importance to utilizing Martian resources. And the experiments that I gave, such as concrete metal extraction, were not meant to be viable for this first mission. They were entirely designed as proof of concepts for the future colonists to work on, which is the purpose of our mission, to enhance the lives of our future colonists. We also claim that fuel processing is a waste of time and not in the mission guidelines. As a byproduct, this process produces breathable oxygen, for one, and further insight into this process and how to refine it, make it more efficient, is going to be crucial for the future colonists that can't afford to bring enough fuel to get back. And so testing it in the safe environment is the safest option. Like, even if fuel production doesn't go as planned, they can still get home. We're going to move on to the next slide here. In our overview, I think a few things were misinterpreted here, and there's also some shakily supported claims that you made. We're going to start with the privacy and the power sources. It is true that we could not place any walls to make, small typo there, between the different sections, and this was due to mass concerns. We just could not afford to install walls in between these sections. But we should have considered something like a plastic drape around the laboratory area to keep it a little more separated. And we should have considered sleeping pods as well to have a little more privacy. And we're probably going to replace our bunk beds with something like this. You claim that we have too much backup power and saying it's a waste of mass, having four 10 kilowatt, 1.5 metric ton reactors. I'm not sure if you had some poor communication in this because you gave two opposite conflicting points. But NASA estimates have shown that about 40 kilowatts of constant energy is the minimum required for the small Martian outpost of 4 to 6 astronauts. So we chose 4 reactors in the event that there was worst case scenario, all solar power goes down. All these reactors could be run on their highest reaction output, and the outpost could still run and keep the astronauts alive. Next, you had some concerns about our greenhouse and our crew size.
You mentioned that our proposed greenhouse was a poor idea as a food source, which I agree with. What I think that Team Solus seemed to misunderstand or didn't hear during the presentation was that the greenhouse was going to be used as a purely testing method, which was mentioned. The idea is to test the possibility of future use of soil. In doing so, we're running all of these tests for plant growth. There was never a plan for this to be a main food source during the mission. Most of our mission plan is based on building for foundations of the future, and finding success in that treatment would change a lot of future Mars missions' food sources. What I was mentioning with the food source thing. We brought more than enough food for the crew to live on throughout the mission, so any failure to grow plants would not put any of the astronauts in critical situation. Like you mentioned in your critique, it is actually pretty much expected for these plants to fail, especially during the beginning of the mission. If the testing of this greenhouse is successful and we are able to use Martian regolith in the future, it would save the crew an immense amount of water that the hydroponics that Team Solos would mention, and it would give a larger variety of food source that hydroponics does not offer, boosting team morale in future missions. And again, this is just first mission testing. It's not meant to be a food source working for the first mission. That's it.
Yeah, like you said, we have supplied enough dehydrated food from Earth to keep our astronauts alive. And a quick thing I don't think I mentioned on the team that did say this isn't from Solus. They claim we didn't have enough variety in our menu. We plan to use NASA's already pre-existing menu of dehydrated foods, which includes a variety of macronutrients and flavor profiles. So sorry about not mentioning that. You claim that a crew size of 4 has no redundancy for illness or death, which is just fully wrong because there'd still be 3 astronauts able to continue our operations. And while that'd be suboptimal, it would still likely work. You say that our rover didn't have a clearly specified crew capacity, which is also wrong. We said it was 2 in the original presentation. And various simulations have not shown that 5 crew members is the optimal amount. And while it is agreed in some circumstances that having 5 people maintains a sense of healthy conflict by having an uneven number of people in the group, 4 astronauts have been used in various space agency simulations and it has shown success. Next, we're going to look at what AD Mars Pioneers mentioned. And they did offer some valid concerns over things which may have been overlooked. Communications between astronauts and Earth. It's true that we did not go extensively into this into our presentation, and we would like to specify that we like to use existing Mars orbiters to relay information back to Earth relays and therefore to Earth. You asked how AI can improve our communications. We're not exactly sure what you meant by this, but we prefer stuff like astronaut logs and observation data to be kept human-made, not generated by AI. No, wrong stuff. As for some approximate power consumptions, I think, especially on the communication equipment, stuff like that. So we have a rough graph describing what we think is important in our terms of power consumption. The ECLSS, or a life support system, will be using about 10 kilowatts an hour, habitat heating about 20, and wind transmitting long-range comms can draw upwards of 2 kilowatts. And then I left some room for other kinds of equipment that would be need to run. Next, we're going to look at some claims that Team Genesis made to us. Quick overview here. We made a few oversights here, but there's some just objectively untrue things about our presentation that they claim. You said that we had no rovers, which is not true. There's a diagram from our original presentation, hand drawn, of the rover concept, but we also had some digital explanations. You said our power system is liable to failure due to only having one power line. And while general external damage to the power line is extremely unlikely due to Martian environment conditions, no dust storm is going to disrupt the flow of power, even if the wire gets covered. We should have mentioned that we'd like to keep some kind of battery supply for the habitat, which could keep it online until the wire is repaired in the event of an unlikely event of malfunction. You said the habitat lacks protection in the event of fire or pressure loss, and we just want to say that foremost, NASA standards, nothing in the habitat should really be flammable in the first place. And while pressure loss is a risk that must be mitigated at all times, even if the habitat was segmented with walls, every door would have to be pressure sealed to prevent casualty in the event of pressure loss, which is just a weight concern that we can't account for at the current moment. But we will maximize risk aversion every way we can. And even, like I mentioned before, in the event of a breaching of the polyethylene dome, the entire habitat would likely not collapse, and there'd be time to fix the issue. Last thing, you claimed us and multiple other teams had no interest in future missions. This is objectively wrong because slides 22 through 33, I believe. Yep, sorry. Are experiments with the direct interest of future colonists in mind. Like we mentioned before, that is the primary focus of our mission. All of our experiments were dedicated towards that. Lola, did you have something to say about that?
Yeah, I can just go a little bit more into detail. Pretty much all of our science experiments were building on future infrastructure and knowledge for missions. We researched Martian soil so that future missions could potentially use that and have a bigger variety of vegetation. We looked into potential concrete so that we could create durable infrastructure that is able to stay on Mars surfaces. And all of our experiments were built on the principle of future use and development. So I'm just not understanding the claim of the lack of scope of future missions. That's all.
Thank you. We're going to move on here to finally Red Horizon. And it's true that we should have supplied a timeline, which is what this critique mentioned, asking for approximate time instead of habitat. I used a industrial grade air pump for a simulation. And to fully inflate the Vectron layer of the habitat, I believe it would take 1 to 1.5 sols on the Martian surface. But halfway through this process, you could begin taking inside equipment due to the fact that the habitat we already have a general amount of structure, including putting down rigid things like the polyethylene barrier and the rigid vinyl flooring. And for transporting certain heavier equipment, it could be put on wheels for easy transport, and we should specify these things. Radiation concerns. We decided that without proper clarifications on the ship that will be taking our astronauts to Mars, we can't confirm or deny they'll be able to take shelter from radiation inside of it. But they'll have their suits on during the setup process, which have a degree of radiation embedded protection in them. And once the polyethylene layer for the habitat is put up, astronauts could use it as a kind of radiation shelter while waiting for the Vectron to be inflated and our habitat to be pressurized. And here is a kind of approximate timeline of how we think the habitat setup would go. And overall, that is, I believe, almost all the critiques that were presented. We might have missed a few. Sorry if we did. I might be able to answer questions in the chat if you had any more. Thank you.
Great job. Thanks. Karoon does have a question in the chat. And is anyone here from Project Ascend? Let's take a 2 or 3 minute pause and see if Project Ascend shows up. So I'll be back in 2 or 3 minutes.
This is the third round defense for the Mission to Mars from the Mars Society project by Team Star Club. Introduction. This presentation will deal with the general critiques that were mentioned by the other teams during the second round of presentations this week. We will focus on the strengths of our mission plan and also focus on the reasons for why we chose our choices for our mission to Mars. Section 1. Lack of radiation protection. Our first point. When choosing a crew of astronauts that were going to be a part of the mission to Mars, we specifically chose a radiation oncologist to help monitor and detect possible signs of radiation sickness. A radiation oncologist is a person who normally treats cancers through radiation, but also focuses on treating different types of radiation sicknesses that people may develop. They will be able to help show or find the first symptoms that astronauts may develop while on Mars and use general treatments that are used here on Earth to maybe help deal with these afflictions. Secondly, our astronaut treatment facility. Our base design includes its own proper section for the health treatment of the astronauts. These include possible treatments such as for radiation sickness or even just other general illnesses. This part of our base is specifically reinforced to block things like radiation, weather conditions, and is regularly sanitized to ensure that no biological compromises happen to our astronauts. Section 2. Lack of planetary defense. Physical attacks to our habitat. Physical attacks such as projectiles or other objects that could cause danger to the habitat would really be of no consequence to the astronauts, as they would be on a life support system powered by our secondary nuclear energy, and then these damaged spots in the habitat could be repaired by the engineer that is in the crew. Dust storms. Dust storms would also cause no real damage to the habitat, as it has already been mentioned that physical damage could be fixed during the dust storm, and effects to our power source, such as solar energy, would also not really be compromised, as we have our secondary nuclear energy source. And then life support systems. Life support systems are an essential part of making a mission to Mars safe and successful in case of emergency. These systems will be in place in our habitat for any emergency situation that may cause compromise in the habitat for the safety of our astronauts in our mission to Mars. Section 3. Lack of geologic research. Our main purpose when choosing our research topics while on Mars was to try and focus to advance as much as possible future opportunities for more missions to Mars to begin a bigger scale long-term mission stay. Studying the surrounding environment with no background knowledge or secondary research team would be extremely dangerous and not beneficial when compared to having a larger scale community of astronauts through a multitude of missions, making exploration much easier and safer for the astronauts overall. Our main purpose when trying to think of research topics was more focused on agricultural advances to support long-term life on Mars, and also things like clean and efficient water sources so that we could also have a sustainable source of water, which we need to live on Mars. That will be everything. Thank you. This is the
Okay, anybody else here from any other team that has not taken their turn, please tell me now. We are waiting on Project Ascend. They are gathering. We will regroup in 35 minutes, take a break, and come back in 35 minutes. Noon Eastern, 9 Pacific time, 35 minutes from now.
Firstly, I will share this script. Okay, Mrs. We will continue in the defending about the battery that we can use in it to bringing uh, ele- uh, our electricity or our energy from kilopower systems, and it is a solid state. It is from a quantum scape company, and is a solid state power or battery. So it's make or it's work with the USA5 type, and all of its descriptions in this magical energy 21.6 watt in hour and cell dimensions and mass and all of these descriptions, and we can show that we can bring our energy from the kilopower to this battery, but uh, if this battery couldn't work correctly, and that will not be doing, um, we can make or we can make a lot of kilopower matrix energy systems, as we talked about it before. So this can bring its energy and the batteries else too. Okay, so this is the first important things after the energy, or after that talking about the kilopower energy. We can show another important things about the or about a material that we can use it in our building, our over, and this is polyether or polyether ketone keto or PEKK. And we can share a very important note about this. The PEKK can be used in some of our parts in our vehicles or in our MMC vehicles, not all of the components or not all of the parts. The part that we can show that it dealing with the temperatures and the rays from the surface or from the sky of the Mars too. And we can show all of these specifications example in this site. And there are a very important thing, or there is a very important thing, that what is tensile stress in the XY direction, in the Z direction, and its specifications. This is the second note. The third note is about how can making polyethyl. And this is the important that our opposite teams defending or making a note to our team about this important thing. The Sabatier response, or if we can take a very important thing, to bring or to make polyethylene that dependent on the HDPE, and we can make it dependent on the HDPE density. This is very important, and all of its types or all of its uh, um, uh, bringing sequentially or things very sequentially, or the things very sequential that are very sequentially, that we can sort it to make the polyethylene from HDPE is first dealing with the Sabatier response. And the Sabatier response, as we can say in this site, is very important on Wikipedia that talking about it. And there are most important, or there are most another important sites or important scientific research, but this is that we can now show it. And in the response mechanism, to work properly with the Sabatier reaction, we can show this function, this pretty function, CO2 plus 4H2 bring CH4 plus 2 H2O. And this reaction or this transfer is very important because we can get the differentiate of the exothermal reaction, and delta H are probably maybe minus 41 kilojoule by mole, by 1 mole. And can be written if this is, we can take the opposite of this response. This is the first, we can know that this is the first thing that we can do, and there are a continuously or another methods to get the polyethylene or the full polyethylene. The second method is the ethylene, or how can build the ethylene. We can build it by crush the methane to bring the ethylene, and that is can make it, or can use it, ethylene, or bringing the ethylene. This is can be made uh, from the function. Yes, there it is. C2H4 plus H2O given CH3 CH2OH, and this is very important. Hydration. This is the hydration function that we can depend on it. I thought that there are another in my scientific research, another I cannot show in it, but I showed in another scientific research. I'm not be sure, but this is the most truly function, and this is 2CH4 react C2H4 plus 2H2, and the both things are related to the hydration. After the hydration, or after the crush, after the crush the methane, we can go to the polyethylene, or political the ethylene that I needed. And this is truly when another reaction to, and this is NC2 or NCH2 equals CH2, and this is in the gas that we can dealing with it. Bring plus CH2 plus CH2 plus in the solid. This is in the solid state. We can political the ethylene in its solid state, and this is very important because we need it political. And delta HIN is equal plus 25% 71. This is the most very important things. I can share now another final screen about the maps, and this is the maps that I can dependent on it. Okay. 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 Yes, this is my application. Okay, this is our pretty maps. I hope that there are any locks. Okay, if we can see that from the screen, now I have my map using the layer that called colorized elevation from the molar. or from my MOLA sensor that can show this map. And if I go to my location that I needed, location is 42 plus minus 42.2 and 74. Okay, 42.2 and 74. So this is my location. I will now share screen. Okay. This is done. Okay, this is my screen, and if we can zoom to my location that I will landing on it, and that is Hellas Planitia. If we can show under this section of my mouse, the deepest region, as we can say, is minus 70 by 70, 85. Yes, this is can read it carefully. We can say it. We can say it very that have very resolution about it. When we draw the lines that will be give out this from the graph, and we can make these things. Okay, this is another line, and after that I will go to the graph or to the view chart. Okay, this is my chart. Okay, this is my chart, and I can slide or I will slide to show the most depending. Yes. We can do another thing in very carefully. Okay. Okay, I can show this. This is the deepest. This is the deepest side. About, if we can show in this graph, -7 by 7, 8. Yeah. This is our region. I thought that it's on on the surface of the left, or in the maximum of the left in this section, but now it don't work properly. So yes, this is our graph. Okay, after that, we can make and play with the layers to show another things in this color map. The color refer to the kilometer or the deepest or the deep regions from its color. From the colorized elevation, we can show this, and we can note about important things that this is layer that name chloride elevation from the molar. So we can show the daytime and the section about this. So as we can show to the thermal inertial and the places that we have amounts of the temperature. So from the test, yes, from the test thermal inertial or crystals. So this is our layers, and with this very important study of these layers, we can get out all of our data, and this surely will be notated it on our notes or on our final study in our notes.
Mohammed, are you almost done?
Yes, Mrs.
Okay, perfect.
Okay. So the last thing that we can show it the layers is we can get the nighttime temperature. Yeah, the nighttime is the most truly thing. Yeah. The final thing that I can show you is if we can get a new layer, there are a new layer that we can get it independent on the ice or the exploration of our ice. We can write ice or water ice resource. Water ice resource, as we can see, is the layer, and the response or this emoji about the layers refers to it. So this is water resource, water ice resource, and we can link it. Okay. As we can see, I can double click here on the water ice resources draw, and I will make a polygon about circle. Yesterday I repaired or I making polygon, but this is don't make me the best things that the circle get it. So I choose it at around the area and okay, and I will take the color map to don't have any problem. No, yes. So I can yes draw. Okay, there it is. Um, okay, he makes some points. Yes. This is the polygon.
Mohammed,
Okay.
you've been speaking for almost 20 minutes. We do have to move on to the next presentation. Are you almost done?
Yes. Thanks, Mrs. Yeah, this is the last thing properly. So thanks. All of our regions that make a circle about it is in the north or in the northwest of Kufstein. And I prepare that it have water ice as we can talked about it before that. And that's all of things. And we can note a very quickly note, Miss, we can share from all of our tables and all of our numerical points in our final study. Thanks.
Thank you very much. Great presentation. I appreciate that. All right, we have project, I believe, Ascend. Is that who's coming up? Project Ascend, are you in the house?
Yes, we are here.
Yes, are you ready?
Do you think you could spare 5 extra minutes for us?
I've been waiting an hour. for you to start?
Okay, yeah. We could start.
Okay, go ahead.
Okay, this is our rebuttal. So first we have the argument against the lava tube settlement. Well, first of all, lava tubes provide extra natural protection against most types of dangers to the astronauts, including radiation. It is also helpful for us for geological science research, as it's easy accessibility to mineral resources as well. And for the structural stability, we can do more research on the regolith density, and we can also hold up the roof while also doing extra research for density. Yeah. And also for the rebuttal to the radiation protection deficiency, the HAB, due to the radiation detection technology, we can have other research towers that we plan to set up in critical locations, also situated in the lava tube underground, which is a natural barrier against radiation, dust storms, and freezing temperatures. Most of the technology also has critical radiation detectors, and will send out packets in case of levels outside the HAB becoming too high. We already have protocols and protectionary systems in place in case of the lava tube collapsing and a part of the HAB being damaged, which extends to radiation. In the case of in the unlikely case of critically high radiation inside all of HAB, we already have spacesuits designed that have radiation protection installed through multiple layers of material that also protects the HAB from radiation. The rebuttal to the lack of science use for the UAV drones. This is in majority a falsehood because the UVA drones not only have LiDAR detection, but they also have ground penetrating radar, allowing us to scan the terrain around crucial zones, especially for the base location for the lava tubes, but also technology to scan the atmosphere with ionizing radiation, radiation level readings, and a way to gather gas samples so that atmospheric magnetization, radiation, and climate research can go along smoothly. Even though the communication towers already have some of these functions, the drones will help us have information for higher up points of altitude and give us a clearer picture of Mars as a whole. Not to mention, these drones will allow us to map safe paths for the rover to gather more information and conduct more sampling more efficiently, experimentations, and of course, emergency and risk discovery when it comes to natural disasters and their likelihood. Of course, there is a point where there's a point made about the design of the drones being simpler, and getting rid of them would allow for more room to be made to study the lava tubes. The design would be downsized. Yes, that is true. But their use case is much too expensive and vital to get rid of these entirely, because since the lava tube research, especially with the properties of the rock found in these tubes, the data is prevalent and the uses has already built into the tab for other purposes. The rebuttal to the lack of science experiments. Once again, the settlement doesn't have much basis in our slideshow. While we weren't able to present most of our science experience, but due to us wanting mostly to present what we had for the UAV designs, the HAB, and the engineering plus safety mechanics, we have 2 experiments each for climate and most details pertaining to that, solar radiation, what it does to the terrain, to the climate and terrain, as well as the composition, geology, and how it affects humans in the long term for settlement, the atmosphere, its composition, and how it may impact human habitation, and etc., and magnetism. When it applies to crustal magnetism, Mars magnetic field, and how these factors above it affect it. We also have all the technology logged for what is needed to complete these experiments, along with some ideas on how the data will be stored and sent back to Earth for further And that's all. Thank you for your time, and sorry about all the waiting.
Are you done? Is your team finished?
Yeah, our team's finished.
Okay. So is there anyone from Red Horizon, Fantastic Six, Red Discovery, Project Aries, or Young Sheldons in the house, in the Zoom? Any other teams? Unmute yourself and let me know.